Hi. In this video, I will talk about the K-mean algorithm, and to explain in detail how it works, I will use the IRIS dataset and the Python libraries of scikit-learn and Panda. So what you can see on the screen is my Jupyter notebook, where I will first import all the libraries that we will need, and then import the data of the IRIS dataset. Here, I also set some colors for the future visualization. So I set the Setosa species in red, versicolor in green, and virginica in blue. I also create a dictionary which will be helpful for visualization, but it's not mandatory. In this dataset, the output are the species of the iris, which are a set of characters, the names, and it might be easier to manipulate if we have digits representing them. So I will transform the text of the species in digits, number. Therefore, we can use an already defined, let's say, function in Python, which is species encoded, which is dedicated to this kind of transformation from text to numerical data. So this is the first transformation of the data that we need to do in order to ease further manipulation. Something that is very important also for the k-means is the normalization, because all the decisions that will be made on this algorithm are rely on distance. So we can use different kind of distance, but it's important that the different attribute of the specimens, here flowers, are normalized, so that if we deal with distance or weight or I don't know, age, all of that can be manipulated in a common way. So I use the a normal function to normalize, which is the standard normalization process, and I will add a new column for those data, so they will not replace the initial data, but they will be added to the Panda framework. So, first step of the k-means algorithm is initialization. The major decision in this algorithm is to determine the number of the clusters. Here it's easy because we know the different spaces that we have in our initial set. We know we have 3 different spaces, and that the whole purpose of our learning methodology is to be able to classify new flower specimen into those 3 categories. For some data, it might be more difficult to identify in advance the number of clusters that we want. So for those cases, there is a further step that we have to do, which is identifying the right number of clusters. But here, it's easy. We have 3 clusters. In the Python implementation of the algorithm, the cluster will be assigned numbers from 0 to 2. And the initialization step is to determine the first centroids of our clusters. So we can either do a random assignation of those centroids, choose some coordinates between 1 and 0, because we know all of our data will be between this interval, because we normalize the data. So here, for instance, we choose randomly 3 points in the space of our initial data. So we have the length and width of petal and sepal. So we have those 4 coordinates for our 3 centroids. We can plot those centroids. As you can see, there are not already existing flowers. There are centroids which are randomly assigned in our space. Here I represented a 2D graph because I think it's easier for human eyes to understand data plotted in 2Ds. And I chose to use the initial data, but it would have been possible to use other dimension, and I will talk about that later on. So this is a random centroids, and we could also set those centroids by choice, choosing to have them as different as possible. So for instance, I can choose those 3 points as centroids. So to dispatch all of the samples, not better, but in a more radical way, let's say. So this is the first step, identify where are the centroids. Then comes the stage of allocation. Each of the specimen, here each of the flowers, must be assigned to one of the 3 clusters. And this will be done by calculating the distance between the flower and the centroid. And the flower would be assigned to the nearest centroid. So in the standard Python algorithm, all those steps are done in one instance, in one function. But here I will really detail all the steps. That's why there is so much code. So here I assign the flower to the nearest centroid. As you can see, we have those 3 colors which represent the assignation of the flowers to the centroids. K-means work with multiple iteration. Each iteration is composed of 3 steps: setting up the centroids, assign the specimen to the clusters, to the nearest centroids, and then update the centroid, the new centroid being the center of gravity of the specimen assigned to each cluster. So all of these steps are done simultaneously when you use the predefined Python libraries. But here I will show you how it works by plotting the movement of the centroids. So the start of the arrow is the old centroid, and the point of the arrow is the new centroid. And as you can see, from the data belonging to each cluster, a new gravity center was chosen. So these steps have to be repeated until the algorithm converge. Here the convergence is measured by the stability of the clustering. If at a given step the cluster composition doesn't evolve, meaning that each specimen stays in the cluster he was assigned to, then we can say that stability is obtained. and that we can stop the iteration. So all those steps are already encoded in the Python library. You can see here how it works. First, you have to import the given library, which is named cluster. Set the number of clusters you want to have. Feed the cluster with the input data, which are the characteristics of the specimens. And then you can store in the format you want the prediction of k-means. Here I have stored them in the ypred vector. You can also store them in a data frame if you want to plot them easier. And in this case, don't forget to name the column, because it's easier to use the column name instead of index, because you never know if it starts with 1 or 0, the index in Python. It's easier if you use names, and it also clear what you are using. You never make mistakes because you have the extended description. You can obtain the number, the coordinate of the centroids, which again are not real specimens, but only center of gravity. And then we can represent the result. Here I've plotted the expected or predicted spaces of the data specimens we have in our database.